Have you ever wondered how a machine, basically a blank slate, goes from knowing absolutely nothing to solving really complex problems? Well, today we're going to follow one. We're going to tag along with a machine learning algorithm, our detective's apprentice, as it goes on a quest to find knowledge hidden deep inside a pile of data.
So that's the big question, right? How does a machine actually learn to think, to sift through clues, connect the dots, spot patterns, and, draw a conclusion? Let's follow the breadcrumbs and see how this whole digital investigation process really works. Okay, so every investigation, every single learning problem, it has to start with a clear brief. The source material breaks it down into three key things. First, you need a task. We'll call that T. That's the job it's supposed to do. Then you need experience, E, which are basically the case files, all the clues it gets to study. And finally, you need a performance measure, P, so we can tell if it's any good at its job. Let's make that less abstract with a classic example. Imagine a program that's learning to play checkers. The task, T, is super simple. Play the game of checkers. Its experience, E, comes from playing thousands, maybe millions of practice games against itself. And its performance, P, that's just its win rate, the percentage of games it wins. See? T, E, P. Every case needs them. So here's our roadmap for today, the training plan for our apprentice. We're going to start with its very first case, see how it learns from clues, and then we're going to watch what happens when the rules get complicated. It's going to need a huge leap in thinking, which will lead it to a master detective's toolkit. All right, it's time for our apprentice to get its hands dirty. The first assignment is the Enjoy Sport investigation. The goal is pretty straightforward. Figure out what kind of day makes someone enjoy their favorite water sport. It's really just a classic case of finding a pattern in the clues. And here it is, the entire case file. This is all the evidence our apprentice has to work with. Each row is a different day, a different clue. Some days they enjoyed the sport. That's a yes. Other days they didn't. A no. The apprentice's job is to stare at this table and find one single rule that perfectly explains all the yes days. Now, our apprentice is a rookie, right? So it's going to play it safe. It uses a method called Find S. The whole strategy is to start with the most specific, most restrictive theory you can possibly imagine. It basically assumes nothing is a yes day unless the evidence forces it to believe otherwise. So this is where it starts. This string of symbols, it's the apprentice's first hypothesis. Each one of those symbols means no value is allowed. It's basically saying there are zero circumstances, none whatsoever, where the sport is fun. It's a total skeptic. It rejects everything out of the gate. But then it sees its first clue, a yes day. And this forces it to completely change its mind. It has to throw out that old skeptical theory. It adopts a brand new one based only on this single piece of evidence. Now its theory is, the sport is only fun if the day is exactly like this one. Then, clue number 2 comes along, and it's another yes day. Our apprentice compares this new clue to its current theory. It sees the sky is the same, the temperature is the same, but wait, the humidity is different. In one case, it was normal, in the other, it was high, but the outcome was still yes. And ding, a light bulb goes off. The apprentice generalizes. It replaces humidity with a question mark, which basically means, you know what? I guess humidity doesn't matter after all. After looking at all the yes clues, our apprentice finally lands on its final theory. It's generalized away the humidity, the water temperature, and the forecast. The simple, kind of elegant rule it's left with is people enjoy the sport when the sky is sunny, the air is warm, and the wind is strong. Boom, case closed. But just as our apprentice is getting a little confident, maybe even a little cocky, the master detective throws it a real curveball. A brand new case that's way more complex. A mystery where a simple checklist just isn't going to cut it. This slide just perfectly captures the new challenge. On the left, we've got our solved case, that nice, simple checklist. But on the right, oh boy, a totally new mystery. How do you define if person X is an ancestor of person Y? This isn't about weather conditions anymore. This is about relationships that can stretch back generations. So to solve this, our apprentice can't just check off boxes. It needs a huge conceptual breakthrough. It needs to learn how to think with variables. To think, not just about fixed attributes, but about the relationships between things. This is a whole new ballgame. And here it is. This is the aha moment. This is what's called a first-order rule, and it's a completely different way of thinking. Let's read it. It says X is an ancestor of Y if X is the parent of some other person Z, and that person Z is an ancestor of Y. Do you see what it's doing? It's defining the concept of ancestor by using the concept of ancestor. It's incredible.
So what's the secret sauce here? Let's break down why this is such a game changer. First, it uses variables. X, Y, and Z can stand in for anybody. Second, it understands relationships, like the idea of being a parent. And third, and this is the big one, it's recursive. To figure out if someone's an ancestor, the rule can just call itself, over and over, climbing up the family tree one generation at a time. This is a massive, massive leap in reasoning.
So how in the world does our apprentice learn to write a rule that's this brilliant? Well, it needs a new tool, a master key designed specifically to uncover these kinds of powerful relational rules. And that tool is called the FOIL algorithm. FOIL's master plan is actually beautiful in its simplicity. The source material calls it sequential covering. Think of it like this. The outer loop isn't trying to solve the whole mystery at once. Its only job is to find one perfect rule that explains some of the clues. Once it finds that rule, it takes all the clues it just solved and sets them aside. Then it just repeats the process on the remaining clues. It solves the mystery one piece at a time.
Okay, so that's the big picture strategy. The inner loop, that's where the real nitty-gritty detective work happens. To build just one of those perfect rules, it starts with the most general idea possible. Something like ancestor XY is always true, which is, of course, totally wrong. Then it meticulously adds one condition at a time, like parent XZ, always picking the single condition that gives it the biggest accuracy boost. And it just keeps doing that until the rule is perfect and makes zero mistakes. By mastering this whole two-step dance, our apprentice is no longer a rookie. It's learned a skill that has a truly profound impact, and it fundamentally changes what a machine is capable of understanding. So why does all this matter? What's the big takeaway? Well, these first-order rules are just incredibly expressive. They can capture complex ideas like recursion that are impossible for simpler models. But what's really crucial is that they're human-readable. We can actually look at that ancestor rule and understand how the machine is thinking. It's not a black box. This lets machines learn about relationships, taking them a huge step beyond just spotting patterns in a spreadsheet. And that kind of brings us to our final thought. The journey from that simple weather checklist to a recursive relational rule, it's just enormous. So if our detective's apprentice can now learn to reason in a way that feels so much closer to our own, what kind of mysteries is it going to be capable of solving next?